Hi everyone, thank you so much for joining our webinar today. Our presentation is on the topic of regenerative grid simulators, how to test smarter, faster, and more effectively. My name is Julie Tran, and I am the marketing manager at Pacific Power Source, and I will be your moderator today. We are really excited to start launching our new webinar series and create more educational topics for you in the future. So please make sure to check back on our website. Now, before we get started, if you have any questions during the presentation, please use the questions chat function located at the top bar, and we'll have time to answer them at the end. When the webinar is over, you'll also see a survey pop up on your screen. We would really appreciate if you could complete the survey so we can continue improving and delivering high quality content to you. Now, I am really delighted to introduce our speaker, Herman van Eikelenburg. He is the product director at Pacific Power Source and has over 30 years of experience in the test and measurement industry. He has held previous roles at Philips, Fluke, Danaher, California Instruments, and Ametek. He has an extensive background in engineering across design, applications, product development, and management, with a heavy emphasis on AC power. He has a wealth of knowledge that we're really excited to tap into. And with that, Herman, I will pass it over to you.
All right, thank you very much, Julie. Welcome, everyone. I would like to start off by explaining a little bit of background about Pacific Power Source. Some of you may be familiar with our company already, but Pacific Power Source has been in business for over 50 years now and has been an industry leader in the power test equipment market worldwide. We provide best-in-class AC and DC power sources, grid simulators, electronic loads with a focus on product innovation, intelligence, and ease of use. Our mission is to innovate the way you test by making it simpler, safer, and more productive and sustainable. In this today's webinar, we will cover the following topics. First, some industry trends and test challenges that result from those trends. The second topic we'll cover is key considerations for selecting a grid simulator. And the final topic will cover some use case examples of using grid simulators for various types of testing. So first, let's explore some industry trends and test challenges created by the ongoing electrification of a wide range of consumer and industrial products. The drive to reduce the use of fossil fuels for power generation and the impact that this is having on the power grid. The expanding range of products that are being electrified drives the need for product testing and validation. Electrification these days is everywhere. Some typical examples you can think of are EV charging at home and at public charging stations, which requires electricity, of course. Diversification to non-fossil fuel-based energy sources like solar and wind, and the associated needs for energy storage to meet growing power demands of the utility grid. Some of these examples are shown here on the bottom. The charging infrastructure that will be needed to support electrification of transportation will be substantial, and that applies to both home charging as well as public charging stations that need to be connected to the grid. And of course, there are a number of associated grid-tied regulatory standards and safety and compliance standards that have to be met by those kinds of products and energy resources that will be brought online in the future to augment the grid and build up the grid capacity over time. This slide here shows some typical distributed energy sources such as solar inverters and wind inverters that come in many shapes and sizes, and therefore various power levels from small systems to large megawatt systems. This slide highlights just some of the various types that exist, such as wind, solar, and battery storage associated with covering energy demands when the sun and the wind is not available. At the same time, a lot of products and appliances and other equipment is being electrified as well. For example, gas stoves being replaced by electric stoves. Those are generally power-hungry devices, take quite a bit of current, and that that will also have to be supported going forward. And those products obviously will all need to be tested for compliance with power grid requirements and other standards that apply to these types of products. All these sources and loads need to coexist on the same electrical distribution grids, of course, which can come from a large central power plant, but also from a variety of distributed resources around the area. If we look at actual power grid voltage and current, it's not always a pure sine wave as it's supposed to be. Power grids around the world obviously have a lot of anomalies that can occur on a regular basis. This slide shows you just a sampling of some of these anomalies that are very typical and common, more so in certain parts of the world than in others, but they generally occur potentially anywhere around the grid in the world. Some of the examples here show voltage fluctuations and variations. There's usually noise riding on top of the voltage. Frequencies can vary and jump and shift. There will be interruptions and power outages and short duration or long duration interrupts or voltage sags, voltage surges, oscillations, etc., and then power surges that disrupt the normal flow of power and electricity to products and units being connected. So these kinds of anomalies need to be validated with your products to make sure they will sustain and ride through those without any damage and any adverse effects, and certainly without any failures. So that's one of the many requirements for product development and test, is to deal with these anomalies. And clearly, programmable grid simulators are the best way to do that, because they can simulate this whole variety of anomalies on the grid under program control or operator control. So challenges from a user point of view, or test engineer or a design engineer point of view, are of course to be able to apply these fluctuations and look at the impact on your unit under test. Can be a production unit, can be a prototype. At the same time, be aware and keep up with evolving standard for grid-related products and grid-related connections, as well as being effective and time effective in testing these and implementing and performing these tests and documenting compliance so your products can get to market. Power levels generally for a lot of products are increasing as more and more products are electrified. Power levels and power demands go up, meaning your power sources and your grid simulators may be undersized, may have to be expanded over time, and having the ability to do that without having to replace your existing equipment can be beneficial over time as your needs grow. And of course, a very important aspect, of course, in this whole context is the accuracy of the operator that's using this equipment. And generally, power outputs from grid simulators are high voltage and high current, so operator safety is of paramount importance, as well as the ability to perform limit testing. And clearly that it requires some knowledge on the part of the engineer, the test engineer, to be able to apply the correct stimulus and the correct tests to verify the standards that are relevant for your particular product. So there are several types of grid testing, as I mentioned earlier, when we looked at all these grid anomalies that can occur on the utility grids. Some of these have to do with pre-compliance, so you may need to do some pre-compliance testing before you go into an actual test lab for final certification, so that you don't have any surprises there, because going to a third-party compliance test lab can be costly, so you don't want to spend more time there than you have to. And having the ability to pre-test these products for these compliance issues is beneficial and cost-effective. For inverter types such as solar and wind, one of the many tests that's required is the low voltage ride through, which is the ability of the energy device to ride through momentary power disruption or voltage sags, voltage drops without shutting down. So there are some requirements for that it has to be able to ride through, and this is what the LVRT test does. Other test requirements, particularly for products being exported to the European market, they have to meet CE mark requirements. That includes, among many things, harmonics and flicker immunity testing for both harmonics and flicker as well as voltage disturbances. So both emissions and immunity test for power grid conditions is required to do, and you can do this pre-testing yourself, and then if you need a certification, you can go to a test lab that's certified and have them rerun the test on your EUT. And therefore, again, pre-testing in your own lab can be beneficial and time saver when you go to the actual compliance tests. Another important issue is interoperability, of course. Does the product work as designed, and does it do this under various line conditions that may not be common or may not be nominal? So limit testing is part of that. High voltage, high frequency, low voltage, any type of permutation. You want to be able to make sure your product is capable of sustaining that. And then, of course, is the product, operating safely? That's obviously a key requirement as well, and part of product design verification. Finally, for some, energy storage, energy generation devices, anti-islanding is a particular aspect that has to do with worker safety of the utility workers. So, if part of the grid gets de-energized for whatever reason, then any, distributed energy resource that is connected to it has to be able to detect that in a timely fashion and stop generating power to the grid so that the grid is no longer energized, and the line workers can go in and fix the problem with the utility that occurred. Without that, their safety would be at risk, and that's obviously not acceptable. So anti-islanding is a very important test for PV and solar inverter products as well. There are many standards, different standards that are relevant to these kinds of product categories. This slide shows some of the relevant national and international standards for PV and wind inverters. They relate to functional aspects such as low voltage ride-through ability, as well as safety-related aspects like anti-islanding. Grid simulators are a key component for this test setup to meet compliance with these standards. And these standards listed here are for various regions. Some are European, some are US specific, some are German, and some are Asian. So there's quite a variety. There are many similarities between them, but they're not necessarily the same. Some use different levels and durations. So it's important to be able to test for various regions where your products will be used or exported to, so that you are meeting the local and national standards of your markets with these kinds of safety requirements. So, and again, being safety related, it's an important aspect of testing your products. Just as a reminder of how many voltage and current and frequency combinations are around the world, this map shows in different colors and different shades and areas what kind of voltage and frequency and permutations and combinations exist around the world. So clearly having a programmable grid simulator that is able to simulate these various grid conditions is important for products that are going to be used in foreign places. So you may not always be able to test at your own facility power voltage frequency permutation. You have to be able to account for all these other permutations that exist in the world. So when it deals with AC power. So grid simulators, of course, do this. They support all kinds of grid permutations, voltage and frequency, as well as power levels, depending on the size of your products, as well as potential for managing inrush current and requirements for different type of load conditions. So that includes the voltage frequency, of course, phasing, three-phase, split-phase, single-phase combinations, depending on what kind of grid connection your product requires, and as well as phase rotations. Positive or negative phase rotation can be tested, with a grid simulator. So international safety standards apply here for compliance testing, and for inrush current, having programmable impedance capability on your grid simulator can be useful to test various inrush conditions as well. So with that in mind, let's explore some of the requirements and considerations for selecting a grid simulator for your engineering lab or your development lab or your compliance lab or your test lab. There are a number of considerations that you have to take into account. First of all, does your product require bidirectional grid simulator? or is a unidirectional just a source sufficient? Depends on the nature of your product. If it's a sourcing capable product, then you need a bidirectional grid simulator. If not, you can do with a regular grid simulator as well. Is it flexible? Does it offer the ability to grow over time? So your initial needs may be a certain level, and over time your products may grow in size and power levels. And is it possible to expand using what you already have, or do you have to replace it at some point if the requirements go too high? So having modular and scalable power can be beneficial in this context. Also, grid simulators obviously have to do AC power. Many of them will also be able to do DC, so it gives you additional flexibility, not only to test for some DC applications, but also look at things like AC plus DC offset issues, as well as testing DC with AC ripples that require both AC and DC. So having that flexibility can be beneficial if you're doing multiple things in your company. Another important consideration is what is the maximum current that you need, and in particular, at what voltage. If you deal with a product that has a variable voltage range capability that operates over a wide range, and it will typically draw more current at low voltage than it will at high voltage. So having a range of current capabilities as a function of the program voltage can be an important consideration, not just the maximum available current of the grid simulator. So it's something to also take into consideration. Another aspect has to do with safety, operator safety. In this case, is the grid simulator output isolated from the grid that feeds it. So having isolation, galvanic isolation in between is an important issue. Allows you to float your EUT away from ground if needed, without having to worry about operator safety issues, and that can be definitely an important decision-making consideration. Another thing to look at, are there additional capabilities and features available on the grid simulator you're contemplating? For example, a lot of regenerative grid simulators may have a load capability or load option, which can be beneficial for other testing you may want to do, as you can use the same product for that. And do you need power hardware in the loop simulation? So does the grid simulator have a PHIL or an HIL interface capability or option? So those can be important if you plan to do those kinds of real-time simulations as well. And then finally, is it easy to use, and it's smart enough to do what you need it to do? So smart control capabilities, convenient interfacing with it, remote control options are all things that you may want to take into consideration. And then another consideration finally is, of course, service and support. Do you have technical support when you need it, and do you have service support when it's needed as well? So is the company standing behind their products not only in the US but worldwide? We mentioned and we touched on this modular and scalable power. So modular systems have the benefit of growing over time. You can start with a certain level, or maybe a single cabinet, and expand over time by adding more cabinets and paralleling together for higher power. So that kind of modularity can be very beneficial. The other aspect is it mobile, especially if it's a cabinet. If it's on casters, it's easier to move around from one location in the lab to another location, and setting it up can be quicker. Power changes, again, growing with future needs is a consideration, and modularity over time. Some of that also makes it easier to maintain and service, or you can, as needed, split a larger system into one or two or three smaller systems and run different tests in parallel. So especially if you transfer from, let's say, the lab to the production environment, that may be an appropriate thing to do. Finally, space restrictions. In some situations, you don't really have a lot of space sometimes, and it can be important to have a smaller footprint. So also matters in case of positioning, especially as these products generally are air-cooled, so they have airflow requirements and clearance requirements, either in the back or the top, and having issues where you may need extra clearance means that you may have a requirement for more floor space than you otherwise would. So looking at airflow considerations and positioning are things to look for as well. So they can be the difference between having enough room or not for a particular type grid simulator. Another aspects that you want to look at is does it have fixed power voltage ranges, or does it have constant power voltage ranges? So constant power ranges, as you see here, combine both high voltage and lower current with lower voltage and higher current capability on the same voltage range. So that means you can test a product that has a wide input voltage capability from the low voltage level to the high voltage level without having to switch voltage ranges if you have a dual range grid simulator. That means you don't have to interrupt the test and switch the unit off temporarily as you switch between different voltage ranges. Usually dual range systems will have to reconfigure when you switch range, and that means they momentarily have to drop the output. So the constant power voltage range does not do that, so you can stay on the same range. So that's definitely a benefit as you can do those wide range, for example, products that run from 120 volts AC to 264 volts AC, and you can test them smoothly over the entire range without having to deal with switching ranges. So that's a typical example. But there are other examples we can mention that constant power range can be very beneficial. Current we mentioned earlier, make sure you have enough current. That doesn't always mean that you just look at the power rating of a grid simulator. It can be important to also compare the rating as a function of program voltage. So the higher the voltage you set, generally the current will be reduced if you stay within a certain power range, the constant power level. So it may or may not be enough for your requirements. So even if the power level between two options may look the same on paper, if you look at the VI curves, you may determine that one can deliver more current at the same voltage, especially at lower voltages, than the other, although they're rated at the same power. And that has to do with maximum current limitations having to do with wires and connector sizes and terminal sizes that may limit the current to no more than a certain maximum. So having the ability to compare those two can be important in making the right decision. So, and if you don't have to oversize more than you need to, obviously you save cost and you have to invest less. So always look at these curves. A lot of products these days are constant power, so there is a curve that's usually provided that shows you what level of current is available at a given voltage setting. So those are important things to check. Another important aspect is the flexibility of the grid simulator to offer different phase modes. And the most common phase modes, of course, are three-phase, split phase, and single phase. And most grid simulators will support three-phase and split phase. They may or may not support single phase. So meaning you have all the power available in a single phase by having three phases in parallel. So that in particular can be helpful if you're also doing DC testing where you may only need one voltage, but you need more current. So in a case of a single phase, you can go to single phase mode and get all that power on a single phase in both AC and DC as you need it. So an important consideration. More sophisticated products will offer more modes. In this particular case, we're looking at the possibility of having two independent outputs that are not connected in any way in terms of frequency or voltage settings. So you have independent control over each output. And the same is true for three independent outputs. So you can effectively use the grid simulator as three separate AC sources or three separate single phase grid simulators, having different frequencies and voltage and current settings on each unit or each output. So that gives you enormous flexibility there. It can be very beneficial in a production test environment where you may be wanting to test multiple products, and if they only require power that can be delivered by one output, then you can test three UTs at the same time with one power source. So very beneficial. Being able to switch between that is important. Does it mean you have to reconfigure, or can you switch under software control? That can be an important aspect to check. And of course, can you have sufficient control over these individual outputs? So can you set the frequencies independently? Can you set the currents independently? That will make it far more useful, obviously. So a lot of flexibility if you have these kinds of multi-mode capabilities. That gives you a lot more output configurations than than just single, split, and three-phase. So, and in some cases, it can be up to 6 different modes of operation. Let's look at a couple of examples of how you would deploy that kind of flexibility. For example, in this case, you're testing let's say a split phase level 2 EV charger, home charger, and you're using 2 phases to connect the 240 volt split phase at the input, and then you use one of the other phases that's left, in this case with a load mode capability option as a load to load down the charger output. So that gives you one power source to do the entire setup. A similar example, for example, could be in a UPS that you're testing by feeding the input grid side with one phase and feeding the other side as a load to load it down, and then test it with just one unit using 2 phases that are separate from each other. So a couple of examples of where that can be beneficial to have that extra flexibility of multiple output configurations. We mentioned earlier safety is important, so and one aspect of that is isolation. So having the ability to have isolation between your grid connection, your facility power, and your units under test, as well as individuals channel-to-channel isolation. So the 3 output phases can be, if they're isolated from each other, they can be at different potentials. So if you use them as 3 separate outputs, they can float at different low levels without having to have a common neutral. So that can be very effective in complex test setups. So doing that in a facility, will give you more operation, more power capabilities, and eliminates the need to add additional external isolation transformers. So this is one of the other benefits you have of making the right selection of grid simulators. So these are important aspects to take into consideration as well. And then, of course, and then finally, we're looking at some flexibility in terms of functionality. So what are some of the possibilities that you can do? Obviously, grids usually use a sine wave, but voltage and current, but in the real world, you want to simulate real world conditions, and they're not always sinusoidal. So having programmable waveforms and arbitrary waveforms is important in this day and age. So you want to be able to create your own arbitrary waveforms or select from a library of preset harmonic waveforms that is provided in a library. So these are things that you want to be able to select, as well as the ability to program transients, and grid simulators usually offer either list mode, pulse mode, or step mode, sometimes all 3, as well as measurements. Having measurements, of course, is helpful for a readback of your current power and energy use, energy consumption, and they are generally all part of the grid simulator function set. So, but having more measurement channels and measurement options gives you more feedback and more ability to document the performance of your EUT, which can be helpful with proving compliance and documenting compliance of your products. So these are functions to look for as well. And then ultimately, it comes down to, can you access these functions? Are they usable? Are they accessible? Are they difficult to get to, difficult to use, or are they intuitive? Are they easy to get, to get the right setup that you're looking for? And of course, nowadays, a lot of products offer, color displays, which are helpful to identify different phases by different colors. So it can be very helpful to have a color display. And front panel controls generally are keypads or knobs. So make things more accessible, but also a remote control capability. So are you integrating it with some other products where you run it off an ATE system? You want to run it off of a software program that you write. You want LAN, you want USB, you want those types of common interfaces to be able to control your source, or some additional ones, depending on the industry you're in, like CAN bus or Modbus, are generally available as an option. Another important aspect can be the ability to control your software, your power source or grid simulator through a web browser. And for that, we offer a Smart Source Suite web browser control capability that's built into the power source controller. So it doesn't require additional software or drivers or anything for you to install. It's ready to go out of the unit itself. So all you need is a browser capable device like a PC or a Mac or tablet or or smartphone, and you have control over all the power source functions that you need from your own device or another device. So very powerful feature that gives you a lot more access to advanced features and complicated setups than you would have without that capability. So here are some examples of that smart suite control browser interface. So obviously you can access larger screens and have multiple windows on the same, if you have a larger monitor on the same display or same tablet. It's real time, so it controls directly, so there's no other software in between. You don't need to write your own software. It's supported through both LAN and USB. If you want, you can use Wi-Fi for it if you have that ability to access it through a Wi-Fi network that you set up in your lab. You can do that as well. And again, it eliminates the need for special software to be installed and updated all the time, or Visa drivers that may be required to run that software. So, and gives you full access to complex functions like transients and waveform creation, etc. So very powerful feature. So let's go to the next slide here. We touched earlier on load options and load capabilities that may be available on your grid simulator. So here are some examples of the benefit of having a load option, especially on a regenerative product like a regenerative grid simulator, as it's able to both source and sink power in both AC and DC modes. You can effectively use it as an electronic load in either mode. So it doubles not just as a source, but also as an electronic load. And being 4-quadrant, it gives you full control over power factor. Phase angle between volts and current can be programmed and controlled, so you can simulate low power factor, high power factor load conditions on your product under test. So this is a fairly powerful feature that you can add to some grid simulators if you want to do both. And then the other feature we mentioned earlier is the power hardware in the loop. It's very commonly used these days for microgrid simulations, where you want real-time simulation of interactions between a number of different energy resources that are connected to the same microgrid. This is done through a real-time simulator, which then interfaces to the grid simulator through a high-speed analog interface. It provides stimulus and response signals. So it basically acts as a power amplifier in that context, but it requires a high-speed interface, not just a regular analog interface like you find on traditional grid simulators, but a very high-speed, real-time analog interface that is sometimes available on certain models as an option or standard. So very powerful capabilities in this kind of simulation environment that are available to you. So in conclusion, let's look over a couple of other things and aspects to summarize some pitfalls possibly to avoid in making your selection. The first one, of course, is you need to have enough power in your lab. So you want to check what kind of facility power you have available in your lab to see what kind of grid simulator you can support. And obviously, a lot of these are higher power, so they require 3-phase power. So in the US, that can be 208 or 480, and other parts of the world is generally 400, 380 to 415. So you want to make sure you have that power and sufficient current capability to drive your grid simulator. So the next thing you want to look at is your space, your test setup, and your wiring. Is there enough room? Can you keep your wire gauges sufficiently high and make sure your wires are not excessively long, especially at AC testing? You don't want to have excessively long wires. They add impedance and inductance that you rather not add if you can help it. So keep those short. And then other things like, are you able to handle loads that kick back energy, such as motors and motor drives and other types of equipment that is not just absorbing power, but occasionally also returning power. Having a regenerative grid simulator will allow you to do that. It'll absorb that energy and put it back on the grid. So it's not only energy efficient and green, it's also capable of handling those kinds of loads that a non-regenerative grid simulator would not be able to handle. They would protect themselves and shut off in those situations. So make sure that if you have those kinds of loads you're working with, that that your grid simulator is regenerative. So programmable impedance is a function that you often use in conjunction with grid testing, so you can look at different grid impedance conditions that may exist around the world. So you can do that with a programmable impedance function more easily than having to insert different physical lumped impedances, which is of course an alternative, but less convenient and less practical. So it's easier to have programmable impedance for that purpose. And then finally, protections can be important. Obviously, current RMS limit functions are typical on grid simulators, but there's other protections that you may want, such as peak current protection, for example, or power protection, and that can both be true power, real power, or apparent power. So you can set limits not just on current, but also on power levels and even voltage. Do you want to protect your UT from overvoltage or check for undervoltage? You can basically make sure your grid simulator does not allow it to go over or under certain test settings and limits. So those are all aspects of protecting the EUT. It can be critically important if you only have one rare prototype that you're working with. So the more you can do to prevent accidental damage to that EUT and prototype that you have, the less time you will lose in your development cycle, because you have to repair and rebuild that prototype that accidentally got damaged, which is not something that is unlikely in some cases. So very important to have those protections. So a lot of things to consider, a lot of aspects to keep in mind when you're looking at these kinds of products, but it's important to do your due diligence before you commit to this kind of test equipment. So let's look at a couple of case test examples. So this example has to do with wind and solar or inverters, or PV inverters or wind inverters, which is very common these days. There's a lot of distributed energy sources these days trying to supplement the grid power as we move away from fossil fuels. So these types of products are subject to a large number of regulatory and safety standards that we showed you earlier on. So they have to be checked against that. They come in power levels as small as microinverters, maybe as much as 200, 300 watts per panel, to string inverters that generally are used for home solar installations or larger systems for industrial solar installations. So the power range can be from a few hundred watts to megawatts. So it's a huge spread that is covered by that. So you have to obviously size your grid simulator accordingly. So a smaller rack mount form factor like you see on the left is convenient for lower power applications, starting at maybe 12 kilowatts and up. A cabinet type system can be better, a higher power system can be better for larger inverters. So it just depends on what kind of size of products you tend to use. So the RGS series that you see on the left is a rack mount model, but it can be parallel multiple units to higher power, which makes it easier to grow over time if you're coming from a lower power level. The GSC series that you see, the cabinet system, is obviously a single floor standing cabinet that comes in levels starting at 30 kilowatts to 55 kilowatts. And those cabinets can be paralleled as well to get to higher power. So you have the ability to grow as your needs increase. General purpose utility testing can be done with either product line as well. They simulate the grid, worldwide grid combinations of voltage and frequency can be simulated at different power and current levels, also parallelable, of course. And load mode options, electronic load modes, are available on these products as well. So they can be used as an electronic regenerative load as well, which is particularly energy efficient when you're using it as a load, because most of the power, about 90% of the power you're dumping into the load will be recovered to the grid. So your energy cost will be significantly lower than when you use dissipative loads, traditional resistive type loads. Another application would be energy storage systems, where you use AC to charge and DC to discharge. So these are very common these days to supplement solar and wind generation for those periods at night or when the wind doesn't blow. So to do a peak shaving of the grid demand, large battery systems are usually installed to cover that. So they will be subject to similar regulations because they are also grid connected. So they have to meet similar requirements as PV inverters and solar inverters. EV chargers are a common EUT these days because of the electrification of the transportation. So there are several levels of these. Of course, there are 3 levels and 4 modes. Different levels of charging give you higher charging speeds, operating at higher voltages and currents. So to test these, you have to size your grid simulator accordingly. Mode 3 is for public charging stations, and they can be higher power. It can be high power AC or more typically fast DC charging, which is the highest power level available for EV charging. So grid simulators that have both AC and DC capability, of course, can be used for DC charging testing as well. So, and they all can be tested on the grid side of things, so because they're all grid tied. So again, quite a range of power levels that apply. So having scalable and modular grid simulators can be very beneficial for this kind of testing as well. And then, again, we saw this earlier, the low voltage ride-through is a very common test for PV and wind inverters. So there are many more standards that are similar to this. So what you can do is write your own. That's one option, or we offer several standards that are ready to go that you can use with our test sequencer. In the smart source browser interface. So you can just load a pre-written test sequence and then just execute it. And those test sequences also give you documentation reports that are generated from it, which is beneficial. But if you want, you can write or develop your own, especially if it's a proprietary standard or an in-house standard. You may want to develop it yourself. And we'll give you a small, example here of how you would go about creating your own sequence, your own test sequence, using a voltage dip example. Voltage dips are very common tested. They are required for CE marking. It has to do with the ability of a product to handle momentary disruptions of the power. It can be dips to 0. It can be dips to less than 100% of the nominal voltage of the grid for a certain period of time, and they have to be applied, at a certain, repetition rate, interval, etc. So for this case study here, we will look at doing one of those dips and see how we can program that on the grid simulator if we wanted to create our own little test sequence for in-house use. So being that we want to do a half cycle in this example, we would use our web browser interface for convenience because it gives us a larger screen so we can see what we're doing. And in this case, I'm going to just need to have a small sequence of a couple of steps that takes the voltage from its nominal down to 0 volts on phase A. And as you see in the middle, I'm only doing phase A. I leave phase B and C at the regular voltage. So I just want to step on one of the 3 phases. This dip. I stayed down for a half cycle at 50 hertz would be 10 milliseconds, but I take 100 microseconds to step it down, to slow it down. So I'm going to stay there for 9.8 milliseconds and then slew back up for 100 microseconds. That'll give me a total of 10 milliseconds. And then I'll just go back to normal. So my dip is done. So this is how you would set that up in a small test sequence list. So transient list, we call that. You can save it for reuse, of course, once you create this little short list. And then when you're ready, you can hit the execute button, say run, and it will basically apply that voltage. So what we're going to do is run it, and then I'm going to capture the output of the grid simulator on the internal scope of the grid simulator. So I don't need an external scope. It'll give me some quick results. So here's the result that you see on the internal scope. As you can see, we got 3 phases in different colors. The blue line is phase A, and I set up a little pre-trigger so I can see the beginning of it clearly. And as you can see, it dipped for exactly half a cycle and then continued on. So trying to trigger on this with an external scope is not as easy because there's only one dip that occurs in many, many cycles. So it's not that easy to set just a trigger level and say trigger on this level, because it would obviously trigger at each cycle, and that's not really what we want. We want to see the one dip that occurs. So in this case, having the internal scope is beneficial because as you can see here, it has a lot of different output or scope trigger functions available one of which is transient run. So because both the scope and the grid simulator waveform generator runs on the same time base, it's very easy for it to cross trigger on these events that it creates itself. So makes it very easy to capture these kinds of rare events that happen very rarely in a long stream of sine waves at exactly the right time. At the same time, we can use the scope to measure and verify that it was indeed the right duration. In this case, it's somewhat obvious to tell because it looks like a half cycle, but you can use the cursors that you see in the top there to position the two cursors around the event and measure the delta t. So it shows you the 2 times and the delta between the two. And sure enough, 10 millisecond half cycle at 50 hertz is what we were looking for. And there it is. So simple example. Of course, you can do this because it's a browser interface. If you have a larger monitor or dual monitors, you can open all these screens, have them available to you for control and looking and measuring in one screen. So you can just toggle, all the screens open at the same time, multiple sessions to the browser interface on the same power source or different ones. So you have a quick overview of all your functionality in one screen, and none of this requires you to write any software. So this is all ready to go out of the box, so to speak. So very convenient user interface. The alternative to this, of course, is for example, in case of IEC-411 immunity testing of voltage, we offer pre-written test sequences that are pre-developed and tested that you can run in the same browser interface using our test sequencer function. The test sequencer function is included. The optional test sequences are available as options, so you can basically buy what you need and load them into your unit, and they're available to use. So much easier, of course, to when it comes to long, complex sequences and things you have to do on a regular basis. So they are a wide range of options available to do many of the AC and grid power related tests that are out there. So that's a quick overview of test capability and test sequencing that is available on our grid simulator. So summarizing the different families that we offer, we have 2 product lines in the grid simulator area. They're both regenerative, so all our grid simulators here are regenerative. So they're bidirectional. The RGS series on the left is our rack mount model. It's a 4U rack mount unit, 19-inch. Comes as low as 12 kilowatts, goes up to 21 kilowatts in this single chassis format. Beyond 21 kilowatt, you can parallel units. You can parallel units of the same power rating, obviously, or if you have 2 different models, you can still parallel them together and they'll add together to give you the sum of the 2 as far as power. So those are modular and stackable or rack mountable. You can use one on a bench, and if you have more than one, you might want to put in a 19-inch cabinet, and we can do that for you as well. So grid simulators that we offer are 15 hertz to 200 hertz, so they easily cover 50, 60 hertz plus all line frequency variations. So and they come with interharmonics and harmonics generation as a standard feature. So other options are the load option that we mentioned earlier, and on the GSC series on the right, the cabinet system, we offer an HIL option as well. So the cabinet systems are 30 to 55 kilowatts in a single cabinet, and you can parallel to at least 440 kilowatts for more capability and more power. So those are the 2 grid simulators that we offer. They all do AC and DC mode, as well as a combination of AC and DC. So they're not AC only; they're more flexible than just AC. So that's the grid simulator series that we offer, 2 of them. The next product line we have are a derivative of those, which is the electronic load models. These are load-only products. So the grid simulator can have a load option, so you can use it either way. Or if you don't have a need for a grid simulator, but you do have load applications, we also offer these as these 2 product lines as that are regenerative electronic loads, the RLS series, which starts as low as 6 kilowatts and goes up to 252 in parallel, or the ELZ series, similar size cabinet as the grid simulator, but strictly used as electronic loads. So similar power levels, additional features, of course, that are specific to loads, such as circuit emulation on the ELZ series, and again, PHIL option on the LZ series as well. So for load applications, again, being regenerative, very energy efficient as well as cost efficient too, especially at higher load levels where you're not dissipating that energy anymore. You're putting about 90% of it back onto the utility. So you can very quickly recoup your equipment investment cost if you have large loads that you're burning in or testing for long periods of time, as you will see some significant energy savings coming back to you. So that's one of the big benefits of using regenerative electronic loads instead of dissipative loads. And then finally, for those of you that have more needs than just grid-related testing, we offer all-in-one products that do more than just grid frequencies. They are wide frequency products. In this case, the AGX series on the left is a 15 to 1200 hertz full power rating frequency range, capable of going to 3000 hertz as well. So definitely suitable for not just grid simulation, but also for avionics testing and defense applications where you're dealing with higher frequencies supply systems than 50, 60 hertz. Same for the AZX series. It's our cabinet system. Again, 15 to 1000 hertz standard range, has a low frequency capability as well, down to from 1 hertz to 15 hertz for some very special low frequency applications as well. So these are all-in-one products. They have all the capabilities of the grid simulator and the loads. Loads are optional for those that don't need the load and just wants the source at high frequency. And again, the AZX has an HIL option, so just like the other two cabinet systems do. So this is a quick summary of the key regenerative product lines that we have available for these types of applications in general use. So with that, I think we are at the end of the formal presentation here. Just to summarize some of our product advantages is high performance and reliability. We have been designing these products for many, many decades, so we are fairly versed in it. We have developed our user interfaces over many, many product generations and years, and have adopted and incorporated a lot of feedback from our customers over the last 50 years into our user interfaces, and are continuously expanding and upgrading our firmware and software as we go. And the customers who bought our systems years ago are still being able to update their firmware to the current versions on some of our product lines. So we do custom solutions as well. If you have special needs, we can review with you and do some modifications and customs specials for your particular needs if they are things that we are able to accommodate. Generally ship fast if you need it fast, we'll do then to expedite. And we have a fair amount of application experience that we developed over time. Not sure what happened there. And customer service with service and application support specialists available online. So that's, I think, the official part of the presentation. So I will now turn it over to Julie for any questions that may have arisen, see if we can answer your questions.
Yes, thank you so much, Herman, for that informative presentation. So we do have some questions that have come in. The first is, does MathWorks kernel-based SpeedGoat real-time hardware work with our grid simulators, including the required high-speed connection?
It does on the cabinet systems with the HIL, because they have a high-speed interface. So it has six readback signals for voltage and current, and 3 inputs for the 3 phases, whatever waveforms you need on the phases and voltages. So it works with different manufacturers, but it will need some adaptation of the hardware interfaces they have. They're not exactly standardized at this time, so you have to have some adapter that connects to the right signals on your HIL system. But it will work with third-party or whatever HIL software systems, SCADA systems that are in use out there. So, and we generally, on a case-by-case basis, try to work with the HIL hardware vendor to make sure the two are compatible and work well together.
Okay, perfect. And then let's see here. Is it possible to use the grid simulator mode and electronic load mode at the same time on a single unit?
It is in mixed mode. If you're in three-phase mode or split phase or single phase mode, all three outputs are synchronized, of course, like you would expect for a grid simulator or an AC source. If you use the independent channel modes, where you have one channel separate from the other channels, because they're isolated, you can do that. You can have different modes on each channel. So you can have one or two channels that are source, and the other third channel can be set to load. So as I showed in some of the examples earlier on, where you're driving an UT on the input side, AC input side, with say one or two phases, and on the output you hook up the third channel and put that into load mode, AC or DC load, and absorb energy from the output of the UT, same UT. So the answer is yes, you can in mixed mode. If you have two three-phase inputs and outputs, then of course you will need two separate units, because now you need six channels and not three. So the answer is yes, yes and no. Yes in some modes, no in other modes.
Okay. And do you have a fiber optic connection interface option to the real-time hardware?
Not at this time, no. We are thinking of looking at that in the future, but at the moment we do not.
Okay. Um, can I parallel two or more grid simulators to get a high power system that don't have the same model and power rating?
You can if they are the same series. So if they are both RGSs, then yes, you can have it. Let's say you have a 12 kilowatt and a 21 kilowatt, you can parallel those and you end up with the sum of the two, so 33 kilowatt. So they don't have to be the same power level. Generally, when customers order larger systems, they use the larger, of the two and parallel the same power level to get to higher power with fewer units, of course, but it's not strictly mandatory. But it's usually if you have multiple units that you bought at different times at different power levels, as long as they're the same series, you can parallel them. Yes.
Great. And how many AZX systems can you parallel?
Typically up to about 8. We could consider going a little higher, but we'd want to do some additional testing. It has to do with the number of units that can, be connected together in terms of the system interface, load capability, and distance. So 8 for sure, possibly a few more. So that's about 440 to about 500 kilowatts right now.
Thank you. Yeah, we can work with all the customers if you have specific requirements for that. Let's see here. Which real-time simulators can be connected to your grid simulators? For example, Opal RT, Typhoon, etc.
Typhoon. Yeah, as long as they're analog I/O, it doesn't really matter in that sense of which hardware you use, but the interfaces, connectors, layouts, and pinouts are not the same between different manufacturers. So each one would require a right adapter, a physical adapter, to make sure you route the right signals into the HIL interface on the power source of the grid simulator. So they can be interfaced electrically, mechanically, but it will require different adapters for different brands of simulators. So they're not. There is some effort to standardize there, but at the moment there's every manufacturer of HIL systems has their own pinouts and connectors. So
Great. And then I think this will be the last question. Does the grid simulator support three-phase, three-line, 200 volt?
yes, I mean the voltage range on the RGS is up to 350 volts line to line, or 600 volts line to neutral, or 600 volts line to line, and so 200 volts falls well within that range. And the same is true for the GSZ grid simulator. It has an even higher voltage range, so you can certainly support 200 volts as well.
Okay, perfect. Yes, so we are at the end of the time now, but there are a few more questions, but we will definitely follow up with you. And if you have any more, please let us know. There is also a survey that will pop up when the session ends. We'd greatly appreciate it if you can complete that for us. And we look forward to working with you and having you join our future webinar sessions. Thank you so much, everyone, for your time. And thank you, Herman, so much for all this information.
Sure, no problem.
Have a great day, everyone. Thank you.